Okay, sir.
Good morning. In this class, we're discussing about the DT-based finite element analysis. As we have to learn about the basic concept of finite element analysis, like a static structure, dynamic structure. Okay, so in this video, we have to connect the what are the general procedures we have to doing for the any common analysis during the finite element analysis. So let's discussing the topic detailing. Let's start.
Hello, hello everyone gathered here. My name is Hari Krishna. Today we're going to see about a prosthetic running blade for our TT topic. As I represent the empathize stage of our design thinking process, imagine you are a competitive sprinter. You train every day. You dream of crossing the finish line first, but you lost your leg in an accident. Does that mean your dream ends? For thousands of athletes around the world, the answer is no. Prosthetic running blades give them back their freedom to compete. Our team choose this as our FEF. Every design decision we make, the material we choose, the curve of the blade, the thickness of each composite layer directly affect a real human being's performance and safety. That is what design thinking means. We start not with an equation, but with the people. So this is the empathy part, and I wish that next part will be a define of the problem segment will be continued.
Yes, sir. So now we'll see the defining of the problem. The problem statement is to design a prosthetic running blade with that could withstand 2.8 kilonewton of dynamic impact load at 3 hertz while maintaining total mass under 400 grams. So the constraint and the boundary condition which we have is that uh, the mass must be lesser than 400 grams and the deflection must be lesser than 15 mm and the factor of safety must be greater or equal to 2.5 and the material must be CFRP material which will be used and the shape of the prototype will be C-shaped blade geometry sketch with load arrows showing foot strike direction and DT stage indicator here will define here we are defining it the problem and I'm here to present define stage and we identified the core engineering challenges. The blade must observe and return energy during each foot strike and the maximum deflection under the load cannot exceed 15 millimeters and factor of safety as I told before it should be greater or equal to 2.5 and the material which we choose CRFP here the candidate material because it offers exceptional stiffness to weight ratio properties that aluminium simply cannot match at this weight class. Our problem is now very clearly defined. Let's move on to our ideas.
Yes, as coming to ideate side, my name is Achan. Where in the side side, we are generated evaluated multiple design concepts using finite element analysis. We consider three candidate material concept used to design a single layer aluminum or a simulation showed it exists mass budgets at 650 grams and gave a factor of safety of only 1.8, unacceptable. Concept B used a titanium alloy, better but still too heavy at 480 grams. And coming to concept C, an 8 layer of CFRP laminate with symmetric layer sequence of 45, negative 5 and 90 degrees.
So let us see the prototype. I am T. Sriniti and I represent our virtual prototype, the FEA simulation results. On screen, you can see the von Mises stress contour planned for our CFRP blade under the 2.8 kilonewton dynamic foot strike load. The red region at the heel curve shows our peak stress of 187 megapascals. Now, this sounds high, but CFRP has a tensile strength of 600 megapascals, giving us a factor of safety of 321, safely above our requirement of 2.5. Compare this to the aluminium simulation. Aluminium reached 312 megapascals in the same location with its yield strength of only 270 megapascals. The aluminium blade would have plastically deformed during a sprint. That is why material selection informed by FEA is not an academic exercise. It is a safety critical decision. Our deflection measured 11.2 millimeters within our 15 millimeter limit.
So myself Nishant, and I close our design thinking journey with a test and validation state. Our FEA simulation served as a virtual test bench. All the designs constraints were successfully met. Mass, which is 310 grams, under limit. Peak deflection 11.2 millimeter, under limit. Factor of safety 3.21, above minimum requirement. First natural frequency at 18.4 Hertz, safely above the 3 Hertz gate loading frequency. So now no resonance risk. Most importantly, design thinking changed how we approach this project. We did not start with equations. We started with human being who wants to run. Every simulation parameters, every material choice was made in service of that person. That is the power of FEA when guided by empathy. Thank you for your attention.
Thank you. Thank you.
Good evening, sir. The meeting